Two telescopes, one on the ground and one in space, at a black hole's jet turn on, enabling astronomers to probe its origin. This artist's concept shows a black hole with hot gas spiraling into it via an accretion disk. Magnetic field lines fling a minute amount of this material into an ultrafast jet that shoots out into space. NASA JPL Caltech. Maybe when you were little, you devised a secret code, such as replacing A with 1, B with 2, and so on. Astronomers use a similar principle to decode the intense environments around gas-guzzling black holes, using different wavelengths to probe what they cannot see directly, at least, not yet. Radio waves, for example, arise from the powerful jets that the black hole sends, shooting outward into space, while X-rays originate in superoplasma, called the corona, closer to the black hole. As for visible light, well, those photons could come from just about anywhere, and that's what makes the code hard to break. Now, astronomers have taken a major step in solving the code, using visible light and X-rays to paint a picture of V404 Cygni, a black hole star binary system, even though it remains a blur in even the best current telescopes. The results appear in Nature Astronomy text available here. Poshakandi University of Southampton, UK and colleagues employed NASA's NuSTAR X-ray satellite and ULTRACAM, a superfast 28 frames a minute camera attached to the Very Large Telescope in Chile, to track emissions from V404 Cygni. The black hole, 9 times the mass of the Sun, pulls away gas from its K-class stellar companion as they whip around each other every 6.5 days. The result is a violently variable system that flares frequently across the electromagnetic spectrum. In June 2015, the whole system underwent an outburst, the brightest seen in the 21st century. Astronomers have monitored visible light variability from black hole systems before, but it's difficult to track where the photons are coming from. They could arise in the gaseous disk that feeds the black hole, the stellar companion that feeds the disk, or the jets that the black hole disk system powers. But the use of X-ray data breaks that ambiguity. Precisely timing changes is critical. The ULTRACAM uses GPS to timestamp images with an accuracy of about 1,000th of a second, 1 millisecond, which was calibrated using observations of the Crab pulsar. NuSTAR gives time measurements of similar accuracy using an onboard crystal oscillator, which is adjusted during contact with ground stations. On June 25, 2015, the team began observing the system with coordinated observations using both instruments. Low-energy X-rays dominated the source's spectrum, and the radio emissions indicated no jet was present. After half an hour, NuSTAR had to stop observing for a brief period as Earth passed between it and V404 Cygni. When the Space Telescope resumed its observations, it was clear something dramatic had happened. High-energy X-rays now dominated, and radio emissions indicated that the plasma jet had turned on. By exactly timing incoming X-rays and visible photons, Gandhi and colleagues discovered that visible light flashes were trailing X-ray flares by just 0.1 second. So the visible emitting region couldn't lie far from the X-ray corona. The photons had to come from the jet. This data paints a clear picture of what's happening in V404 Cygni. Gas stolen from the companion star mostly feeds the black hole, but strong magnetic fields fling some of it away into a superheated, X-ray-emitting corona. This region may serve as the base of the black hole's jet. The gas then accelerates, flowing 19,000 miles down along the jet, where it radiates visible light. These 3 stills from an animation show the launch and acceleration of a blob of plasma down the jet first frame, its travel down second frame, and its passage through a standing shock, where it brightens again. The animation may be downloaded in .mov format here. Cosmovision W. Stephen Gandhi had previously studied another stellar mass black hole, GX 3394, which displays a similar 0.1 second delay between X-ray and visible light flares. The region that lies between the corona and the visible light, between the X-rays and the visible light, is critical to understanding jets. This is the unseen region where plasma accelerates by a sight unknown means. Astronomers hope to refine models for jet powering mechanisms using the results of this study, said study co-author Daniel Stern, NASA JPL. The results mesh nicely with previous studies of the supermassive black holes BL Lacerty and PKS 1510089, says Alan Marsher, Boston University. Even though these black holes are millions of times more massive than V404 Cygni, the distance between their X-ray emitting and visible emitting regions is the same if you take the differing masses into account. But that doesn't hold true for all objects. The supermassive black hole at the center of the galaxy M87, for example, appears to defy the rule. The devil, it appears, still lies in the details of our understanding of black holes and their jets.